Welcome to Organic Chemistry. Today we're going to think about Sn1 and E1 reactions. That means S substitution, N for nucleophilic and 1 for first order. So what do those things mean? Substitution means changing one thing, one substituent, for a different one. Nucleophilic means the nucleus, the carbon atom in this case, positively charged, is attacked by something. So we consider our organic species to be the reagent, and a nucleophile comes along, something that can attack a nucleus. So a negatively charged species comes along and jumps onto it. And for one, meaning first order, that would mean if we change the concentration, the rate of the reaction only changes by the same factor as the concentration. So if we halve it, it halves, and if we quarter it, it quarters. Whereas if it was second order, it would be squared. What does that tell us? That tells us that if we change the concentration of the other reagent in there, if there are two reagents, if we change the concentration of the other reagent, nothing happens, as long as there's a little bit in there. We'll go over to the board and show an example of this. We have this trimethyl iodide, so it's got three methyl groups on it and an iodine. The reason for the iodine will become apparent later when we discuss how easy it is for these things to come off. This is reacting with OH minus, and it's forming this alcohol, which is tertiary butyl alcohol. So it's methane, ethane, propane, butane, and it's tertiary because they're all connected to one. Primary would just be all in a row. Secondary would be a fork, and tertiary, it has three on one, so this is a special type of carbon. Those are particularly good for this type of reaction, which we will also be getting into shortly. So the first thing that is interesting is the first orderness. That means that only this reagent and not this reagent has an effect on the reaction, and that tells us something fundamental about the mechanism of the reaction. It tells us that there is a hidden step in here. This OH minus doesn't react with this species. If we look at our tertiary butyl iodide, our 1,1,1 trimethyl iodide, we can see that it has one group that's different, and the iodine is going to drop off in the reaction, and that only that is determining the rate of our reaction. So if we can break that down into two steps where the iodide comes off first and then the OH goes back on again, we can see the following reaction scheme, and we can consider this tertiary butyl iodide turning into this carbocation, this positive species, and then, oops, my screen has gone off, you're still on, and then it turns into this, whoops, it's not quite on your, so let me move it up a little bit, OH, it turns into that, oh, it's not quite there. So that's this is our product, the alcohol. If we imagine that this process here is fast, and this process here is slow, and that there's a massive difference in rate between the two, then we can generate the effect that we see, that the rate is determined by this. So if we change the concentration of OH minus, it changes the speed of this reaction, but because it's so much faster than the first reaction, we get apparent first order, that it's only determined by the concentration of the first species. I keep looking down because my other screen keeps going off. The part of this reaction, the first part of this reaction we'll look at, we're forming this thing that I've called a carbocation. So it's a carbon and it's a cation, so we can call that a carbocation, and it's forming this iodide ion. Now we can think about the stability of these two products effectively, because this really happens. This is an intermediate. So if we stop the reaction, we can isolate this. In effect, this is a two-step reaction, but because the second step is much faster than the first step, there's only ever a very tiny amount of this in here. They're actually both reversible reactions, but we play with the concentration of the hydroxide to make it go in this direction if we want to make the alcohol. So if we imagine the orbitals here, the bonding orbital between this iodine atom and this tertiary butyl group is this group here. So this is full of electrons. This orbital here is full of electrons. The anti-bonding orbitals will be on the outside, but this is an orbital full of electrons that's holding the iodine and the molecule together. If we take the iodine away along with its 2 electrons, we can draw that by putting a 2-headed arrow on there, which denotes that the 2 electrons in the bond both go to the iodine. If we draw a 1-headed arrow, that would mean one of the electrons goes, and then we would have an I0 species and a neutral carbon species, and they'd have 1 electron each. That's quite difficult to do, so it's much more likely that we take both electrons, and if we take both electrons, we end up with what we see, the I-, which we can measure after the reaction, so we know that that happens. So it's much more likely that that happens in the first step. These bonding orbitals are sp3 orbitals. They're tetrahedral sp3 orbitals, so there would have been a little lobe on the back, but the bonding part of it is the bit in between, and the anti-bonding part is a bit on the outside. But when we've taken away the iodine, it can rehybridize into sp2 plus p. So this is sp2 orbitals, and they are planar. So this is a triangle of methyl groups, and it's all flat. And then in the other direction, so sticking out and in, or whatever way we want to do it, if we have it flat this way, it's left and right, we've got a p orbital, and the p orbital is completely empty. There's nothing in it. We can consider that it's positively charged because it's got space in there for electrons that could go in. So if electrons are going to be donated to this atom, that's where they're going to go. The other thing that I wanted to talk about at this point is the stability of these 2 species. So what I want to mention right here is a fundamental stability question: which species are more stable than others? And it turns out that the more space that a chemical can spread out charge or unbalanced electrons over itself, the better. So if we take the bottom case, we've got fluorine, chlorine, bromine and iodine, and they get bigger as we get further along because we're going down the periodic table. So in simple inorganic chemistry terms, we've got 2 shells, 3 shells, 4 shells and 5 shells, partly filled, or completely filled, sorry, when we got the iron. And so the atom is getting bigger and bigger and bigger, but it's still only 1 charge. It's still only 1 total of charge, and so the density of charge goes down as we go bigger and bigger and bigger. That is good because it means that well, it's not good, but it's a thing. It means that iodine ions are more stable than fluoride ions, iodide ions and fluoride ions. This also tells us something about hydrogen fluoride, for example. Hydrogen fluoride is not as acidic, hydrofluoric acid is not as acidic as hydrochloric acid. And hydrobromic acid is more acidic than hydrochloric acid because the ion is much more stable on its own, so it's more likely to form the anion. So if we go out of water and into ethanol, for example, it's much more easy to protonate our ethanol with iodic acid than it is with hydrofluoric acid. Hydrofluoric acid is known to be particularly hazardous, and that's partly due to it going around as an HF molecule instead of breaking into an H plus and an F minus, and as a non-polar, or as a polar but not so polar molecule, it can get through our skin more easily than an ion can. Looking at the cation, the carbocation, we see another similar effect, that the methyl groups can push electron density, so they push a bit of charge towards the positive charge. We can see this in two ways. We can either imagine that the carbon is slightly weak, and so it can lose electrons. They can be sucked towards this black hole of electrons, the positive charge, so they can be pulled towards it, which makes a slight negative charge on the end of the molecule. Or we can see it as a spatial effect, that this orbital, where the electrons actually are hanging around, because there aren't any electrons anywhere else, it can interact with this positive lobe, the empty orbital, so it can donate a little bit of electron density, which is analogous to a double bond, but it's not a full bond. It doesn't break and join in completely, but all of these hydrogens can in turn push a little bit of electron density into this positive charge. There has been discussion over which effect is more strong, whether there's a through space effect, whether there's a bonding effect, what it really is. But what we need to know is these methyl groups are helping to distribute the positive charge out onto the outside of the molecule. It's a positive ion, a carbocation, but it's stabilized by distributing the positive charge around the molecule. Just like this negative iodide ion is stabilized by being big, this is stabilized by spreading it out over the molecule. Spreading it out is a critical part of organic chemistry. We could do the opposite, so we could make it worse by putting something else on there that will suck electrons away. We will look into that at a different time. So if we put on a electronegative group over here, like an oxygen or a fluorine or something, the fluoride is unlikely to form because the fluoride ion is very unstable, it's very small. So even if we had a fluorine and an iodine on, it would be unlikely to form the fluoride ion, and it would make it less likely to form the iodide ion because the positive species would be unhappy, because this positive would be not shared with the fluorine. It would be made worse because the fluorine is trying to draw electrons away from a carbon that doesn't have very many. So that's going to be unstable, or better said, is going to be more difficult to happen. It's going to have a higher energy barrier to form it, so it'll be even slower than normal. That's why we use this example, because in this example it works. There's another reason why. It's symmetrical, and so we don't see anything weird happening. So if we consider the next step, that's where the symmetry comes in important, because our hydroxide ion can attack with a double arrow, because it's putting both of the electrons in. It can attack into the orbital, into this empty orbital, from this side, or from this side. But because it's symmetrical, we get the same product, hence making it easy to start with. But we would theoretically get two products. So if we now write on here A, B, and C, so this would be, I've drawn it, yeah, okay, this is A, this is B, and this is C. I've done it anti-clockwise, I should have done it the other way around. But anyway, depending on which way we attack, we get the two isomers, the two optical isomers, the two chiral isomers of the new product, which is ABCOH, depending on what these are. Obviously we would have to label them with something, so we could make this an ethyl group, this a maybe an ethyl chloride, and this something else, just so that we can, or this can be a methyl group, so that we can see the difference when they react. Then if we've got 4 different substituents on our central molecule, we will then get 2 products. They're the same chemical, but one of them's in one direction, one of them's in the other direction. So if we're going to form, if we're going to form a chiral molecule, we must be aware with this mechanism that we will get at least 2 products, both of the enantiomers of this carbon center, because its shape is now lost. There's no difference between the 2 sides. So let's have a look at how good some of the groups are that we can put on there, how good they are at leaving. We like to call that a leaving group because it's the group that's leaving. So our iodide in this case would be the leaving group, but we could choose other molecules. So we could choose a fluoride or a chloride or a hydroxide group that could be leaving, and those have different leaving group effectivities, leaving group powers. Some of them are better than others. So if we look at the halogens, as we go down the group, as we had before, they get bigger and bigger and they become more and more stable, and so they are easier to make, and so we generate our carbocation more easily. If we have a hydroxide group, sorry, I said this once already and I got confused, so I'm trying again. If we take a hydroxide group, and here we're trying to get that to leave, it's not a very good leaving group because it's not that stable and it's got to leave into solution. And in an organic solution, for example, OH- is a terrible ion. It's too small, it's too charged, and it will try to remove protons from things. But if we add a strong acid, which I had already added, I did it once already. So if we had a strong acid, we can protonate this oxygen on the lone pair, one of the lone pairs that sits over here, and then we can lose water, and water is an excellent leaving group. So we can turn a not very good leaving group into an excellent leaving group. So if we take that reaction that we had at the beginning, this molecule here going to this molecule here, if we add acid to it, we tend to get more over this side. And if we have basic conditions, we tend to be more over this side, because the OH- is obviously a bad leaving group in basic conditions, and water is an excellent leaving group in acidic conditions. And then we tend to get, just statistically, because it's going backwards and forwards, we tend to get to this side. The other thing that came up in that argument is the solvent, just accidentally, but the thing that comes up accidentally is the solvent, because the solvent is going to interact with the ions that we make. So if we have an ion, so we're going to make an iodide ion, for example. If we have an iodide ion and it is that on the screen? If we have an iodide ion and it's, oh, I can't see. If we have an iodide ion and it's in a non-polar solution, it's going to be incredibly unstable. Our carbocation is also going to be unstable, and so it will be comparatively difficult to make it. If we have it in water, for example, the iodide ion is very stable because it will interact with the water very strongly, and the carbocation is reasonably stable because it will interact with the oxygen negative part of the dipole and be stabilized. We obviously have to get it dissolved into the water though, and our trimethyl iodide, for example, is not very stable in water. It's not going to dissolve. So we have a problem. If we have a slightly less polar solvent, so an alcohol, for example, we can get this to dissolve, but obviously the alcohol might interact as well. So we now have a new problem. Which solvents are we going to use? the more polar they are, the more likely we are to be able to stabilize our ions. And the less polar they are, the less likely they are to stabilize the ions. And we have a new problem arising from that. We have a new problem arising from that, that many polar solvents can act as a base. If we take water as a polar solvent, it can take a proton to form H3O+, and so it can act as a base, and that will tend to drive the elimination reaction instead of the substitution reaction. So if we have the first reaction, which was this turning into this, and we do it in water, some of the elimination reaction will happen because the water can act as a base. Whereas if we do it in acetone, for example, acetone is a polar solvent, but it isn't very good at accepting protons. It's not a very good base, and so it can't, so it doesn't promote the elimination reaction as much. And so we can consider the two possibilities driving the two types of reaction, making the whole reaction more likely, making formation of the carbocation more likely, and making the elimination more likely compared to the substitution, because these will always compete with each other. I think that was enough input for one time, so I'm going to leave it there with Sn1 reactions and E1 reactions. We will look at Sn2 reactions and E2 reactions next time, where there are contributions to the kinetics from both of the starting materials effectively. So we would have a very similar type of reaction, the products are very similar, but the mechanism is different. Then we can look at which products we get if we have a more complicated molecule where different protons could be removed to form the elimination product, or where different molecules could leave, or where the Sn1 and the Sn2 mechanisms could both occur. Those will make it obviously very complicated, so we'll start off with Sn1 so we'll start off with Sn2 and E2 next time, and then we will consider when they win and when they lose, when we get the worst possible case for organic chemistry, which is a mixture of all things. That is obviously something that we as preparative chemists, or those of us that do preparative chemistry, try to avoid at all costs, because it is making life difficult for us. Usually the starting material isn't expensive, but cleaning it up, if we've made lots of dirty other things in there, if we make lots of side products, is a problem.